Hello, I welcome you all to this another interesting screencast. The problem reads, if the soil exerts a trapezoidal distribution of load on the bottom of the footing, determine the intensities W1 and W2 of this distribution needed to support the column loadings. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we have a footing and we have the reaction at the bottom of the footing it's a distributed load, trapezoidal distributed load, or it's a combination of a triangular and rectangular distribution force load. And we are now being asked to determine this W1 and W2. So that at the end of the day, there is equilibrium. All right. So what we need to do is, since we have two unknowns, W1 and W2, we need a minimum of two equations. And since we want this reaction force from the soil to equilibrate with the forces on the columns, we are going to use, of course, the equilibrium equations. So use the summation of forces in the vertical direction as well as take moments, summation of moments about any point. We can choose any point. So let's say I choose this point as my point A. Right. So let me divide this load into two parts. Let's say from here to there like so. That's one rectangular load. And then we have triangular like so. Great. So we have two loads. So we need now to represent this particular load as equivalent forces. So let's have one equivalent force for the rectangular like so, and let's have one for the triangular. All right, and then let's have the locations also. The locations, there we go, something like that, and at the very end there something like that. So that position, that position, that position, and that position. Okay, so let's label this. The first one, the red, is of course the area under the load diagram, and the length of this is that's 1 plus 2.5, that's 3.5, plus 3.5, that's 7, plus 1, that's 8. The whole length is 8. So this is going to be equal to W2, that's the intensity times the length times 8. So this gives us 8W2. Then this one, the triangular, we are going to subtract W1 from W2 since we are interested in this length here, right? This height rather. So this is going to be equal to W1 minus W2 times the length. So at half, okay, this is triangular, times W1 minus W2 times the difference, of course, half times the difference of W1 and W2 times the length, which is 8. Therefore, this gives us a 4 W1 minus W2. Oh, great. And then these particular distances, let's start with a rectangular. It's just half of 8, so it's just half of 8. Okay, and half of 8 is just equal to 4. And then a triangular, this is going to be equal to 1/3 of 8. 1/3 of 8, which is just going to be equal to 8 over 3. Okay, therefore this one in between here, so we have that's 8. So if this is, let's subtract. This is 8 minus 4, that's a 4. And then we have a 4 minus 8 over 3. If we are to write this like so, this becomes, that's a 12 minus 8, that's a 4 over 3. I want to write them as ratios, as fractions, so that I don't lose the accuracy. Okay, so we'll have summation of forces equal to 0, and we apply the equations of equilibrium because we do not want this particular body to fly in the vertical direction. So it has to be in equilibrium, and therefore the forces in the vertical directions have to be equal to 0. So we have minus 16, minus 80, minus 50, and a plus 4W1, minus 4W2, plus 8W2 equal to 0. Alright, so this becomes equal to minus 60, minus 80, minus 50 is minus 190, and 8W and minus, that becomes is 4W1, then plus 4W2 equal to 0. So this is our first equation. Let's make W as W1 as subject of formula, subject of the formula. So W1 here is going to be equal to 190 divided by 4 minus W2, which is going to be equal to 190 divided by 4. This gives us 47.5 minus W2. Let's take moments about point A. We also expect moments to be equal to 0 at any point, so that this particular body does not rotate. So we are going to have a 60 by 1 negative, then minus 80 negative also by 3.5, negative 50 by 7, and then we have positive moment, which is 4W1 minus 4W2 times 8 over 3, and then we have a plus 8W2 times 4 over 3 plus 8 over 3, so this is a 12 over 3, and the 12 over 3 is just a 4. Okay, that's a 4, and this is equal to 0. So if we were to simplify this, we'll have minus 60 by 1, minus 80 by 3.5, minus 50 by 7. So we have a minus 690. Okay, and then we have a plus 4W1. This becomes a 32 there, a 32W1 divided by 3, and a minus a 32W2 divided by 3, and a plus 32W2 equal to 0. Right, so we are going to replace this value that we just found We'll replace this value here. Okay. Once we do so, we have 690 plus 32 divided by 3. And then we have a 47.5 minus W2 minus 32 divided by 3 W2 plus 32 W2 equal to 0. Therefore, our W2 is just going to be equal to, you can calculate directly. So say minus 690 divided plus 32 times 3 times 32 divided by 3 times 47.5. Okay. Alright, take it the other side, then divided by we have a 32 divided by 3 as a minus, so say minus 32 divided by 3 minus 32 divided by 3 and then plus 32. Okay, 32 divided by 3, 32. Okay, then we close brackets. So we get a 17.1875. I'll write everything. So the units are kilonewtons per meter. Alright. C17 1875. Therefore, our W1 is just going to be equal to minus 1 plus 47 times we are just subtracting 40. We are just saying we are just using this equation here, this equation. Okay, so this gives us a 30. This gives us a 30.3125 kilonewtons per meter. Right. So this is about it. Let me just outline the final solution. So we have W2. Okay. W2, and we expect W1 to be higher. Like so. Great. So these are the intensities of W1 and W2 of this distribution needed to support the column loadings. Or these are the intensities that are required to maintain equilibrium in this particular system of loads. I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.